So before we get on to Wien's displacement law, I just want to discuss a bit what actually happened here. So this is actually a perfectly fine calculation. I looked back. I actually did do the question somewhere separate, but I put the thing wrong. So that's why I might have sounded slightly confused with it. This temperature of 158 Kelvin is actually okay. It could be the temperature of a neutron star, for instance, because they tend to be pretty cold. Anyways, so Wien's displacement law. So this is to deal with the relationship between the maximum emitted wavelength and the temperature of that particular star. And it's linked by this formula here, lambda equals beta divided by capital T, where beta, again, is another constant. It's 2.897 by 10 to the negative 3 meter kelvins. Meter kelvins? Meters kelvins? 2.897 by 10 to 3 meter kelvins. Why not? Or meter by kelvin. It doesn't really matter dimensionally too much. So this beta constant is actually, it doesn't actually have a name. When I was actually discussing this, when I was learning this first, I tend to call this Ben because, it's because it's funny giving letters names, but also because the beta, I tried to think of a funny name for it, and so I just called it Ben. B for Ben, beta for Ben. So we're going to be using this formula in conjunction with the thing we learned previously, the answer we got previously, to find that peak emitted wavelength of the star.